Welcome to The Explainer. Today, we're bringing some serious energy to a truly fascinating concept in data science. We are going to completely demystify the inner workings of a support vector machine, or SVM. At its core, an SVM is just this incredibly powerful algorithmic tool that mathematically categorizes the world around us. And by the end of this explainer, you're going to understand exactly how this spatial logic works to classify data points, and you'll see exactly why data scientists rely on it to seamlessly slice through massive, complex data sets.
Okay, let's dive into this by anchoring the complex math in a very relatable, everyday experience. Imagine you're at a local fruit stand. A kid picks up a bright red fruit and asks, "Hey, is that an apple or a strawberry?" Now, it takes the human brain literally just a couple of seconds to process that visual information and categorize the fruit as a strawberry. But how do we train a computer to make that exact same distinction when it's handed completely unknown data?
Well, to answer that, we have to look at where SVMs actually fit into the larger picture of artificial intelligence. SVM is a specific method that falls right under the umbrella of supervised learning. And supervised learning just means we actively teach the model by feeding it historical, pre-labeled input data. So we give the computer a bunch of images already tagged as sweet strawberries and another batch tagged as crispy apples. Once the model is trained on those really clear examples, it can take a brand new, totally unlabeled piece of data and accurately predict which category it belongs to.
Drawing the perfect line.
Now, as colorful and tasty as that fruit example is, let's look at a slightly more complex, numerical example to see how the math actually operates behind the scenes. Instead of fruit, imagine we're mathematically classifying men and women based entirely on just two data points, their height and their weight. If we plot those on a 2D graph, we're going to get two distinct clusters. To separate them, we obviously need to draw a line down the middle. But if we just randomly eyeball a dividing line between those clusters, we end up with a low margin of separation, and that severely increases our chance of misclassification when new data arrives. So, to predict effectively, our algorithm seeks the optimal split. It's looking for a line that guarantees the maximum possible empty space, or margin, separating the two classes.
To find that absolute perfect maximum space, the algorithm zeroes in on very specific data points. We call these the support vectors. You can think of these as the extreme points in our data set that sit right on the very outskirts of their respective groups. In our height and weight example, these support vectors would be the shortest men or the tallest women in our sample. Basically, the outliers sitting closest to the opposing cluster. They are absolutely the most crucial pieces of data because they literally anchor and define our entire boundary.
So, the crucial takeaway here is that the boundary line drawn between these support vectors has a specific technical name, a hyperplane. While it looks like a simple flat line on a 2D graph, when you start dealing with multiple dimensions of data, it becomes a literal plane of intersections. The optimal hyperplane is precisely positioned so that it maintains the maximum possible distance away from the support vectors of any class on either side.
The math to find this optimal hyperplane is conceptually brilliant, but honestly, it's beautifully simple. We just take the shortest distance from our boundary to the closest positive support factor, and let's call that distance d+. Then we take the shortest distance to the closest negative support vector, and we'll call that d-. When we add d+ and d- together, we get our total distance margin. The SVM algorithm constantly calculates this sum, shuffling its boundary around until it finds the exact position that makes this distance margin as large as mathematically possible.
The kernel trick transformation. But here is where we run into a major dilemma. What happens if our data isn't perfectly separated into two neat little clusters? Imagine a scenario where one set of data occurs squarely in the middle of another set, kind of like a cluster of blue dots completely surrounded by yellow dots. A simple, straight hyperplane literally cannot slice through that data without making massive errors. When data is trapped like this in the middle of a one-dimensional or two-dimensional input space, the SVM applies what's called a kernel function. This function elegantly lifts the trapped data, translating it into a higher dimensional output space. A 1D line of overlapping points is transformed into a 2D curve. A completely surrounded 2D cluster is lifted into a 3D array. Suddenly, by simply adding another dimension of depth, what was impossible to separate on a flat surface can now easily be sliced cleanly by a flat hyperplane. The advantages of SVM. You can really start to see why this specific spatial logic is so highly revered in the machine learning world. Before we jump into writing actual Python code to see it in action, we really need to understand the unique power this algorithm holds over other classification models. The first massive advantage is how gracefully SVM handles high-dimensional input space. A lot of algorithms suffer from what's called the curse of dimensionality, when variables scale into the thousands, but SVM naturally adapts. For instance, when tokenizing text documents, an SVM can effortlessly process sparse document vectors containing upwards of 2.4 million different tokens. And finally, the SVM features a built-in regularization parameter, often referred to as lambda. This mathematical feature naturally stops the model from overfitting, meaning it prevents the model from becoming too perfectly biased to its specific training data. That allows it to remain highly accurate when judging new, real-world data.
Classifying crocodiles and alligators.
Okay, we're going to step into a practical Python use case. Picture a family at the zoo, looking at a reptile enclosure. A young kid points in and asks, "Hey, is that a group of crocodiles or alligators?" The dad, being a total data science enthusiast, decides to turn this into a learning moment. Instead of just guessing, he decides to let a support vector machine mathematically segregate the two reptilian groups. To build our model, we obviously need physical measurements to differentiate them. First up is size. Crocodiles tend to be generally larger, while alligators are somewhat smaller. Second is snout width. Crocodiles have noticeably narrow snouts, whereas alligators sport wider ones. These two distinct measurements, overall size and snout width, will act as our x and y coordinates.
Now, as dedicated as we all are to data science, jumping a zoo fence to physically measure the snouts of dangerous apex predators is probably a terrible idea. So instead of risking life and limb, we are going to use the number 40. In our Python setup, we'll utilize a tool from the sklearn library called make_blobs. This incredibly handy function allows us to safely and instantly generate 40 lines of random simulated sample data. That gives us 20 data points representing our alligator cluster and 20 representing our crocodile cluster.
And this right here brilliantly illustrates the absolute elegance of modern machine learning. Despite all the complex multidimensional geometry, optimal margins, and kernel tricks we just discussed, the actual code required to build and train this linear model in Python comes down to just 2 lines. Line 1 calls the SVM function and tells it to use a linear kernel. Line 2, using the fit command, maps our random 40 data points, our x coordinates, and our y labels right into the model. With literally just those 2 lines, our hyperplane is created and our model is fully trained.
All right, once the model is trained, it's time to test it with the unknown. We're going to feed in 2 sets of brand new, completely unclassified snout and size measurements. Our new data inputs are the coordinates 3, 4, and 5, 6. We send these fresh numbers into our trained algorithm using the Python predict function.
Instantly, the algorithm plots those new coordinates against the optimal hyperplane it generated earlier. It evaluates exactly which side of the boundary those points fall on, based on the distance margins it established, and our output is a simple binary, a 0 and a 1. The model has successfully, and mathematically, predicted that the first set of measurements belongs to an alligator and the second set belongs to a crocodile.
From drawing simple boundaries between apples and strawberries, to cleanly slicing through multidimensional spaces to categorize millions of text documents, support vector machines offer an incredibly robust and geometric approach to supervised learning. We've seen how elegant the underlying math is and how beautifully simple the implementation can be. So, as we wrap up this explainer, I'll leave you with this question. Armed with the power of maximum margins and kernel tricks, what complex, high-dimensional data will you classify next?